Right at this moment, while you are listening to these lines, something has just happened that almost no one on Earth knows about. A machine the size of a small car is drifting through the space between the stars at 21 billion kilometers away from Earth, and it has just received a string of commands it has never received in nearly half a century of operation. That string of commands requires it to shut down simultaneously many systems that are keeping it alive and turn on replacement systems that have never been activated at this distance, all at the same time. This is not a new spacecraft. This is not a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the scientists studying its data were even born. The signal from Earth takes 18 hours just to reach it. If the string of commands succeeds, it buys more time to live. If it fails, the fuel lines freeze, the spacecraft loses control of its orientation, the antenna turns away from Earth, and nearly half a century of exploration ends in permanent silence. No recovery, no second chance. The engineers at NASA do not use words like maintenance or upgrade to describe this procedure. They call it the Big Bang. And this is the story of Voyager 2. And this is the part that the headlines do not tell you. It is not just that NASA has just bet a 49-year-old spacecraft on an untested procedure, but the reason they chose Voyager 2 to try first, instead of Voyager 1, says something even more frightening than the risk itself. Inside the old data from this spacecraft, there is a secret hidden for 34 years that science has only just discovered. It is the only spacecraft in human history that has ever seen Uranus and Neptune with its own eyes, and no one has been funded to go back there again. And if the procedure succeeds, it opens up the possibility of resurrecting a device that has been turned off on Voyager 1 itself. Stay with me, because by the time this story ends, you will never look at those 2 points of light, called the Voyagers, in the same way again. I am Jack, and this is where we dig deep into the stories that science has not fully told. Subscribe right now if you want to hear more, because we have only just begun. Let us begin with a paradox that almost no one realizes. If you go on Google right now and type the word Voyager, almost every result is about Voyager 1. The farthest spacecraft, the most famous spacecraft, the spacecraft that is about to reach the 1 light day mark from Earth. Voyager 2 has almost disappeared in the shadow of its sibling. But if you ask any planetary scientist, not the headline writers, but the people who actually sit and work with the data every day which spacecraft has seen more, has gone to more places, and left a bigger scientific mark, the answer is not Voyager 1. Voyager 2 is the only spacecraft in all of human history that has flown past all 4 giant planets: Jupiter, Saturn, Uranus, Neptune, not because it is more powerful or better designed than Voyager 1, because the 2 spacecraft are almost identical down to every screw, but because the universe gave it a window that no one could create with money or technology. In the mid-1960s, a NASA engineer discovered that the 4 giant planets were about to line up in a way that would allow a spacecraft to use the gravity of each planet like a slingshot to the next one. This alignment happens every 175 years or so. The previous time was during the era of Napoleon. The next one is around the year 2153. The 1977 window was the only chance in the lifetime of anyone alive. NASA assigned Voyager 1 2 planets, Jupiter and Saturn, assigned Voyager 2 all 4. And here is what most people do not know. Voyager 2 was launched before Voyager 1. On the 20th of August 1977, it left the launch pad at Kennedy 16 days before Voyager 1. It was named number 2, not because it launched later, but because its trajectory to Jupiter was slower. Voyager 2 is the older brother, not the younger one, and its grand tour is one of the most extraordinary journeys that human engineering has ever carried out. Jupiter in July 1979. The Great Red Spot at that time was nearly twice its current size, suggesting the largest storm in the solar system was gradually shrinking. But the real challenge was not taking pictures, but threading the needle through space. For the gravity assist to work, Voyager 2 had to pass through a corridor only 150 kilometers wide to hit the exact aim point to the second, while traveling at 10 kilometers per second. Slip by a few seconds, and the gravity assist fails. Gravity assist fails, and the whole chain Saturn-Uranus-Neptune dies with it. The grand tour ends before it truly begins. The result, Voyager 2 arrived at the Jupiter aim point 0.4 of a second late, off by 60 kilometers. Over a journey of hundreds of millions of kilometers that was threading the needle in the dark. Saturn in August 1981. Then the green light, Uranus, Neptune. 12 years past 4 planets, each planet using its gravity to fling Voyager 2 to the next one, each time faster, each time farther, each time deeper into the untouched parts of the solar system. After Neptune, Voyager 2 did not stop. It kept flying straight outward. In 2018, it crossed the Heliopause, the boundary where the solar wind dies out and the protective bubble of the solar system ends. Voyager 2 became the second spacecraft in history to step outside everything we call home, but in a different direction from Voyager 1. And what it measured when it crossed that boundary together with what it left hidden in the data from Uranus for 34 years did not match any model anyone had ever predicted. Imagine you live in a single house in the middle of an icy desert. The house has one fireplace, only one. That fireplace generates electricity to light the lights, run the computer, run the radio for communication, and also radiates heat to keep the water pipes from freezing. Each year it grows a little weaker. It cannot be repaired. It cannot be replaced. It cannot be refueled. You can only choose to turn off some lights to stay warm or reduce the heat to keep the lights on. And if one day the temperature drops too low even once, even for just a few minutes, the pipes freeze permanently. The house dies. That is exactly how Voyager 2 is existing. Its only power source comes from 3 radioisotope thermoelectric generators containing plutonium-238 that create heat as they slowly decay and then convert that heat into electricity, not a fission reactor. Just plutonium that is shutting down according to the laws of physics that no one can negotiate with. When launched in 1977, they produced about 470 watts, losing about 4 watts per year. 49 years later, about 220 to 250 watts remain. But the number more important than total watts is the thermal margin, the distance between the temperature of the hydrazine lines on the spacecraft and the freezing point. That margin narrows every year. And hydrazine is the fuel for 5 small thrusters that keep the spacecraft oriented. They rotate Voyager 2 at a rate of 0.3 degrees per second, so slow it takes 5 minutes just to turn 90 degrees. But that very slow rotation is what keeps the high-gain antenna always pointed at Earth. To know its orientation in endless space, Voyager 2 uses a sun sensor to lock the spacecraft axis on the sun and a star tracker to lock the rotation axis on a star of known brightness. When both are locked, the spacecraft knows exactly where it is pointing. But all of it only works when the thrusters are still running. The thrusters only run when the hydrazine is still liquid. Hydrazine is only liquid when the lines are warm enough. The lines freeze and the thrusters die. The thrusters die and the antenna drifts. The antenna drifts and there is permanent silence. In 49 years, the engineering team at JPL has step by step turned off devices, step by step, reduced the heat, step by step, pushed the house closer to the freezing line. 7 out of 10 science instruments have been shut down. Everything easy to cut has been cut. There is nothing easy left. That is why what NASA has just done to Voyager 2 is something that has never been tried in nearly half a century. I need to tell you why Voyager 2 is still so important, that NASA is willing to bet it. The answer does not lie in what the spacecraft is doing right now, but in what it did 40 years ago, and no one knew until very recently. On the 24th of January 1986, Voyager 2 flew past Uranus at a distance of 81,433 kilometers from the cloud tops. For 45 hours as it flew past, the magnetometer continuously recorded data. The data was transmitted back, analyzed, and published. The conclusion at the time was that Uranus had a strange magnetic field, but the magnetotail region behind the planet was nothing special, boring. The dataset was filed away, and for 34 years, no one looked at it with fresh eyes. Until the year 2020, when 2 space physicists at NASA's Goddard Space Flight Center, Gina DiBraccio and Dan Gershman, decided to load that exact dataset again. Not because they suspected anything had been missed, but because both were planning future missions to Uranus and wanted to know what questions to ask when they got there. They changed only one thing. Previous studies read the data averaged every 8 minutes. DiBraccio and Gershman zoomed in on every 1.92 seconds. The smooth curve from 34 years earlier suddenly turned into a jagged, spiky line, and in that spiky mess they saw a zigzag signal lasting exactly 60 seconds. 60 seconds in 45 hours of flyby. A needle in a haystack. Gershman looked at DiBraccio and asked, "Do you think that could be a plasmoid?" DiBraccio ran the data through the analysis pipeline, and the result came back clean. "I think it definitely is," she said. "Imagine the magnetic field of a planet like water flowing through a faucet. When the planet spins fast, centrifugal force pulls a portion of ionized atmosphere outward, and the magnetic field wraps around that portion, forming a bubble. When the bubble gets big enough, it pinches off from the magnetotail and flies out into space, carrying away material from the planet. Like a droplet shooting off the end of the faucet when you turn it too fast." Gershman described how centrifugal force dominates and the plasmoid pinches off. What Voyager 2 happened to fly through was a plasma bubble filled with ionized hydrogen 204,000 kilometers long and 400,000 kilometers wide. The magnetic field inside had the smooth, closed-loop shape characteristic of a plasmoid created by the planet's own rotation. The conclusion of the paper, published in Geophysical Research Letters, was that Uranus is losing its atmosphere through these giant magnetic bubbles. Estimates suggest the planet may have lost between 15 and 55% of its atmospheric mass that way, more than Jupiter or Saturn. This was the first detection of a plasmoid in the magnetosphere of an ice giant planet, and no one knew for 34 years. DiBraccio said, "Imagine if a spacecraft only flew through this room and tried to describe the entire Earth. It would not tell you anything about the Sahara or Antarctica, a discovery that changes our understanding of an entire planet hidden in 60 seconds of data from 1986. The question you need to keep in mind from here is how many more secrets are still lying in the data that Voyager 2 is still sending back every day. And if the spacecraft dies, what do we lose? But here is the part that makes the plasmoid story more than just interesting science. That discovery tells us that Voyager 2's data is still generating new findings 34 years after it was collected. The dataset that the entire scientific community thought had been fully mined turned out to still hide things no one thought of because no one had looked closely enough. If that is true for old data, then it is even more true for the new data that Voyager 2 is still sending back every day from the space between the stars. Keeping the spacecraft alive means keeping the chance alive. Losing the spacecraft means losing it forever. And when I say forever, I want you to understand the real scale of that word. Voyager 2 is the only direct in-situ data source that humanity has about Uranus and Neptune. No other spacecraft has ever been there. No other spacecraft is on the way. The Planetary Science Decadal Survey 2023 ranked the Uranus Orbiter and Probe mission as NASA's #1 priority. But that mission has not been funded, has not been designed, has no launch date. Even if it launched today, it would take about 13 years to reach Uranus. The gap between when Voyager 2 dies and when a new spacecraft arrives could stretch 2 to 3 decades, possibly longer. And that is not all. Right now, Voyager 2 is measuring interstellar space from a completely different direction than Voyager 1. 2 spacecraft, 2 directions for 2 measurement points in 2 different regions. That is the only way to know whether what Voyager 1 discovered is a universal phenomenon or just specific to the region of space it passed through. Lose one spacecraft and you lose the ability to compare. Lose stereo and you have only mono. And with mono, there is no way to know if what you are seeing is the whole picture. If you think losing Voyager 2 is a distant concern, then listen to what happened 3 years ago. In July 2023, the engineering team at JPL sent a routine command string up to Voyager 2, an operation they had performed thousands of times over nearly half a century. But this time, one command contained a programming error that caused the high-gain antenna to drift 2 degrees off from Earth's direction. 2 degrees? If you tilt your head 2 degrees, the person facing you would not notice. But at a distance of more than 19 billion kilometers, 2 degrees means the signal completely misses Earth. Voyager 2 went completely silent. Not corrupted data transmission like the Voyager 1 incident. Silence. Not one bit. Not one signal. And the scariest part is Voyager 2 did not know it had a problem. The sun sensor still locked on the sun normally. From the spacecraft's perspective, everything was fine. It still thought its antenna was pointing correctly. Only Earth knew there was a problem because it received nothing. The team sent commands up and waited 18 hours with no response. Sent them again and waited 18 hours with no response. The only solution was a gamble. The Deep Space Network station in Canberra, Australia, used the largest antenna in the Deep Space Communications Network to send an extremely powerful blind command straight into the region of space where Voyager 2 was located, hoping that even with the antenna off by 2 degrees, the signal would still be strong enough to slip through the edge of the reception angle. The command had only one purpose: to reset the antenna orientation back toward Earth. They sent it and waited more than 18 hours for the signal to travel. The spacecraft processed it, more than 18 hours for the response to come back, more than 36 hours for one round trip. The blind command worked. Voyager 2 reset its antenna and pointed back at Earth. The spacecraft lived, but the lesson could not be clearer. One small programming error, 2 degrees, nearly lost the only spacecraft that had ever flown past 4 planets. Keep that in mind because here is what comes next. Voyager 2 nearly died because its antenna drifted 2 degrees, and now NASA wants to shut down 3 heaters on that very same spacecraft all at the same time. Additionally, there is one more discovery from Voyager 2 itself that you need to know, because it changes the way we understand the shield that is protecting the entire solar system. On the 5th of November 2018, Voyager 2 officially crossed the Heliopause, the boundary where the solar wind runs out of energy and the protective bubble of the solar system ends. It became the second spacecraft in history to step into the space between the stars, but it stepped in from a different direction than Voyager 1, and that is what made the difference. Because after Voyager 1 crossed the Heliopause in 2012, scientists had the first picture of what the boundary of the solar system looked like. They expected the second time would confirm that picture. Voyager 2 would measure similar numbers in a different direction, and everyone would nod and say, yes, our model is accurate. That did not happen. Voyager 2 measured a heliopause that was completely different at almost every level. In terms of distance, Voyager 1 crossed the boundary at about 119 astronomical units from the Sun. Voyager 2 crossed at about 121 astronomical units. The bubble is not perfectly round. It is lopsided, thicker in some places, thinner in others, like a ball that has been squeezed off center. In terms of the magnetic field strength jumped suddenly when Voyager 2 left the solar system and entered the local interstellar space. But the most surprising discovery was that the north and south poles of the Sun's magnetic field and the interstellar magnetic field were aligned with each other. No one had predicted that. And the numbers were also different from Voyager 1, showing that the buffer region between the solar system and interstellar space is not uniform, but broken into many pieces with different strengths at different locations. In terms of cosmic radiation, right when Voyager 2 crossed the boundary, the amount of galactic radiation surged. The data showed that the heliosphere bubble is blocking about 70% of galactic cosmic radiation, keeping it from reaching the solar system. And when Voyager 2 passed through the heliosheath, the buffer region, right before the boundary, it detected leakage pockets, locations where radiation increased abnormally, even inside the bubble. The shield has cracks. And finally, there is the plasma. At the Heliopause, the plasma temperature jumped to 30,000 to 50,000 degrees Kelvin. The density is still low because this is still space, but the existence of extremely hot plasma at the boundary of the solar system, almost like a wall of hot plasma, is something that models predicted could happen, but not to this degree. Scientists were stunned because the temperatures were much higher than expected. So why did Voyager 1 and Voyager 2 see such different things at the same boundary? One hypothesis is the 11-year solar cycle. NASA uses the metaphor as if the sun is breathing. When activity is strong, the heliosphere swells. When it is quiet, it shrinks. The two spacecraft crossed the boundary at different phases of the cycle, so they saw different shapes of the same bubble. And there is one more discovery from November 2024, when a research team from JPL and the Max Planck Institute reanalyzed Voyager 2 data at Uranus and found that right before the spacecraft flew past the planet in 1986, an unusual solar wind event had dramatically compressed the planet's magnetosphere. If Voyager 2 had arrived a few days earlier, it would have seen a completely different Uranus. Everything we know about that planet could have been distorted by a cosmic coincidence. Two discoveries, both from the same spacecraft, both changing our fundamental understanding of the solar system and the shield protecting it, and both are the reason NASA decided not to let Voyager 2 die without taking the bet. And now the story returns to the present moment. Because everything I just told you about the plasmoid, about the heliopause, about the hot plasma wall, and the shield with cracks, all of it comes from a spacecraft that is slowly dying. And the event that pushed everything to the point of no return did not happen on Voyager 2, but on Voyager 1. On the 27th of February, 2026, Voyager 1 was performing a routine rotation maneuver to calibrate its magnetometer instrument, an operation the spacecraft had done many times. But this time, the power level suddenly dropped for no clear reason. It dropped close to triggering the low-voltage protection system. That system is an automatic mechanism from 1977. If the voltage drops too low, it will automatically shut down components in its own priority order, not the order the engineering team wants. Recovery from that would take many weeks, possibly many months at a distance where every command takes 23 hours to arrive. It might not be recoverable. Kareem Badarudin, the Voyager mission manager at JPL, compared it think of fault protection like a safety net for a tightrope walker. It is there, but the performer should never let go of the bar. Fault protection puts the spacecraft into a safe state, but we have to recover from that and get back on the bar. The JPL team did not wait. On the 17th of April 2026, they sent a command to turn off the LECP on Voyager 1, the low-energy charged particle instrument that had been operating continuously for nearly 49 years. It measures ions, electrons, and cosmic rays, providing data about the structure of interstellar space that no instrument on Earth can replace. Turning it off bought about one more year. Only 1 year. Put that decision in context. The Voyager 1 cameras were turned off in 1990, right after taking the final image. The pale blue dot. Earth seen from 6 billion kilometers of faint blue dot in a ray of sunlight. That was the last image Voyager 1 ever took. Since then, the team has turned off devices one by one over decades. Each shutdown is a set of questions that will never be answered. Each shutdown is a part of the spacecraft dying permanently so the rest can live a little longer. The LECP on Voyager 2 was turned off in March 2025. Now the LECP on Voyager 1 is also off. Each spacecraft has only 2 to 3 instruments left from the original set of 10. And this is when the engineering team realized what they knew was coming but was not easy to accept. The old approach of shutting down one device at a time had reached its limit. Everything easy to cut had been cut. Every non-essential heater had been turned off. Every system that could be switched to power-saving mode had been switched. There was nothing easy left. If they wanted to extend the mission, they needed a completely different solution, not cutting more, but restructuring how power flows through the entire spacecraft. They needed something that had never been tried in nearly half a century of operation. That is when the procedure named the Big Bang was put on the table. This is what NASA internally calls the Big Bang, and when you understand how it works, you will understand why that name is not a joke. The idea sounds simpler than reality. On Voyager 2 right now, there are 3 devices keeping the hydrazine fuel lines warm for the thruster system. Those 3 devices work well, but they consume power. The plan is to turn off all 3 at the same time and turn on 3 replacement devices that do the same job of keeping the lines warm, but consume a total of nearly 10 watts less. 10 watts. Less than an LED light bulb in your bedroom. But on a spacecraft living on its last watts, 10 watts is the difference between 1 more year of scientific data and permanent silence. And the reason they call it the Big Bang is because it all has to happen at the same time. They cannot turn off the old heaters one by one and then turn on the replacements one by one. Because if they turn off an old heater before the replacement is on, even for just a few minutes, in those few minutes the temperature of the lines could drop below the hydrazine freezing point. At interstellar space temperatures, a few minutes is more than enough. And if the hydrazine freezes, then you have already heard this chain of consequences. The lines freeze, the thrusters die, the spacecraft loses the ability to rotate, the antenna drifts away from Earth, permanent silence. At a distance of 21 billion kilometers, no one can go there to fix anything. There is no reset button, there is no manual override, there is no second chance. This is not the first time the JPL team has squeezed every watt out of Voyager. Earlier, they had switched Voyager 2 to a backup thruster set for the rotation axis, a set built in 1977, and never turned on during the entire flight. The goal was to turn off the heaters on the lines leading to the primary set, saving about 12 watts. The backup set worked. That tactic extended the mission by many years, but the Big Bang is the next step, and it is much bigger. Not 1 heater, but 3 at the same time. Not 1 replacement component, but 3 replacement components. The risk multiplies many times over, and it cannot be reversed. And now we come to the part where the story shifts from engineering to something else. NASA chose Voyager 2 to try first. The public reasons are that Voyager 2 is closer to Earth, so the response time is shorter, and it has a little more power, so the safety margin is larger. Both reasons are true, but there is a third reason that no one at NASA says outright, even though everyone understands it. If the procedure kills the spacecraft, losing Voyager 2 is considered less catastrophic than losing Voyager 1. Voyager 1 is farther, more iconic, approaching the 1 light day mark in November. In the cold calculations of engineering triage, when you have to choose which spacecraft to risk first, you choose the one that, if lost, hurts less. But pause for a second and think whether losing Voyager 2 would really hurt less. This is the only spacecraft that has ever flown past 4 giant planets. The only direct data source about Uranus and Neptune, the spacecraft that is measuring interstellar space from a direction no one else is measuring, the spacecraft whose data from 1986 still generated new discoveries in 2020. Less catastrophic does not mean not catastrophic. The schedule is to try it on Voyager 2 in May and June 2026. If successful, the team will try it on Voyager 1 as early as July, and if Voyager 1 also succeeds, then there is a real possibility that the LECP, the instrument just turned off on Voyager 1, can be turned back on. Because the JPL team deliberately left the stepper motor inside the LECP still running. A small motor consuming only 0.5 watts that rotates the sensor so it is ready to operate again if there is enough power. The door to resurrection is still open. It just needs enough power to step through. So has the Big Bang succeeded yet? As of the moment you are listening to this video, NASA has not announced the results of the Big Bang on Voyager 2. May has passed. June has passed. That was the time frame the JPL team set for the testing and implementation phase. But there has been no announcement, no update. When the press sent follow-up questions asking about the current watt levels on both spacecraft, about the impact of the Big Bang on the remaining active instruments, about the expected remaining lifespan, JPL did not respond. Silence. And silence from NASA can mean many things. Maybe they are processing the data and not ready to announce yet. Maybe the procedure succeeded and they are preparing to announce. Maybe they encountered unexpected problems and are working to fix them. Or maybe the procedure failed and they are assessing the consequences. No one outside JPL knows. What we do know is that if the Big Bang succeeded on Voyager 2, then the team will try it on Voyager 1 as early as July. That is right around the time you are listening to this video, and if Voyager 1 also succeeds, then the LECP, the instrument just turned off after 49 years of operation, might be turned back on. That possibility exists because of a small but intentional decision by the engineering team. When they turned off the LECP, they deliberately left the stepper motor inside the instrument still running. That motor consumes only half a watt, rotating the sensor in a circle so it is ready to operate again anytime there is enough power. Stamatios Krimagis, the principal investigator for the LECP at the Johns Hopkins Applied Physics Laboratory, wrote that the stepper motor had operated flawlessly for nearly 49 years and over 8.5 million steps. And amazingly, it continued stepping after we turned off the supplemental heaters to save power, and its temperature dropped to negative 62 degrees Celsius. This is the stuff dreams are made of. Matt Hill, the new principal investigator for the LECP, also at Johns Hopkins, said that we hope the latest plan from the Voyager engineers will allow us to turn the LECP back on for Voyager 1 so we can continue to learn about any surprises waiting for Voyager in these distant regions of space. But he also added that they have a good track record of performing power-stretching miracles, but eventually this chain of successes will end. Eventually this chain of successes will end. That sentence is worth hearing twice. But while we wait for answers from JPL, let us talk about something that no answer can change. Because regardless of whether the Big Bang succeeds or fails, there is one truth about Voyager 2 that no result can change. When Voyager 2 flew past Neptune in August 1989, the navigation team did something they had never tried before. Instead of approaching from behind, they pointed the spacecraft right in front of the planet and had it fly over the North Pole. The reason was Triton, the largest moon orbiting on a tilted path, and the only way to fly close to it was to bend the trajectory downward using the gravity of the planet itself. In exchange, the grand tour ended there, with no way to use Neptune for any further speed boost. But humanity got to see Triton for the first time. 5 hours after passing Neptune, Voyager 2 flew past that moon at negative 235 degrees Celsius. Winds on the parent planet reached 2,400 kilometers per hour, the fastest ever recorded in the solar system. The great dark spot, large enough to swallow Earth whole. 5 new moons, 4 new rings in a single flyby. At Uranus, Voyager 2 captured Miranda, a small moon with canyons deeper than 19 kilometers, whose surface looked as if it had been torn apart and reassembled in the wrong order, possibly the remnant of an ancient collision. At Saturn, it captured close-ups of Enceladus, an icy moon with an old cratered region sitting right next to young, smooth plains, suggesting geological activity right beneath the surface, all from a single spacecraft. The closest image humanity has of Neptune is from 1989. 37 years ago, the Uranus orbiter mission has not even passed the proposal stage yet. The alignment that allows a grand tour like that will not happen again until around the year 2153. No one alive will see a second chance. In about 40,000 years, Voyager 2 will fly within about 1.75 light-years of the star Ross 248, continuing to drift through the darkness as a reminder of a civilization that once dared to send a machine beyond everything it knew. Attached to its body is a gold-plated copper disk, containing the location of the solar system encoded with pulsar coordinates greetings in 55 human languages, 90 minutes of music from cultures throughout human history, and sounds of rain, falling ocean waves, human laughter. Voyager 2 has carried that record through 4 planets and then into the darkness between the stars, through more places than any object humans have ever created. And now that spacecraft, the only one, is waiting to see if the 3 replacement heaters will work. And now let us put all of this into the bigger picture. In November 2026, Voyager 1 will reach the distance of 1 light day from Earth. Send a command Monday morning, receive the response Wednesday morning. No object humans have created has ever been that far. Voyager 2 is behind it, traveling in a different direction. The 2 spacecraft are mapping interstellar space from 2 points. New Horizons is expected to enter interstellar space around the year 2038. If both Voyagers die before, that there will be more than a decade with no one measuring anything. In the early 2030s, the radioisotope thermoelectric generators will fall below the minimum threshold. The final signal will arrive. After that, silence. That is why 10 watts matter so much. This is what I want you to take away. NASA is betting a 49-year-old spacecraft on an untested procedure to save 10 watts, less than a bedroom LED light bulb. But those 10 watts are the difference between 1 more year of data and permanent silence. The spacecraft threaded the needle through a 150-kilometer corridor at Jupiter, flew over Neptune's North Pole, discovered giant bubbles hidden in 60 seconds of data, crossed the Heliopause from a direction no one had measured, survived a 2-degree antenna drift, and is now waiting on 3 replacement heaters. There is something that no amount of money, technology, or time can recreate. That is 49 years of momentum from a machine that has endured everything it was designed to withstand. At a distance of 21 billion kilometers, 3 heaters off, 3 replacements, on confirmation signal taking 18 hours back to Earth. The JPL team could bet or give up, and they chose to bet. The question is whether anyone outside them is paying attention. If this story is what you came here to hear, please subscribe and turn on notifications. Share this video with someone who needs to hear it, because this story deserves more than the silence it is receiving.